Hello, everyone. Thanks very much for joining this topical meeting, this IRIS-HEP topical meeting on large language model and general AI tool usage in particle physics to try and accomplish interesting and useful tasks. This is the first one we're having. I highly doubt this will be the last, given that this is a super active area in the field right now with lots of interesting papers being written and results coming out. Today we just have a collection of 3 talks in different areas from people that are known to the Institute who have been doing work on this, but as I mentioned, we're anticipating more. We're gonna go ahead and kick it off with our first talk from our very own Gordon Watts on vibe plotting. We're going to try and keep talks to under 20 minutes, and then we're also going to have any relevant discussion be tightly scoped to follow afterwards, given that some of our speakers need to move on to other responsibilities and meetings of the day. So please go ahead and hold your questions until the end of each section, and then we'll quickly go through them in Zoom just by raising your hand on Zoom. So without any further ado, I'll turn it over to Gordon and let him kick us off.
Okay, can you see this full screen? Did I get the right screen?
Yes, very well.
Perfect. Thanks. All right, so first of all, I apologize. This time is right up against a class I have to teach. So I am going to end up not seeing everybody's talk, and this is an area I'm really interested in. So please, it is not an editorial comment. It is just my unfortunate term this quarter means I have very little spare time in the morning because of teaching. Okay, so I'm going to talk about some work I started actually last June. So it started it's been almost a year. I'll spare you the context, but the basic idea has been how far can we get with a set of prompt files and use some of the tools that actually access an experiment's data or open data to make plots. Okay, so that didn't work. Okay, so just first for a bit of context, Matthew already mentioned there's been a bunch of interesting papers lately, and I have a smattering of them that really pertain to particle physics, starting with this Agents of Discovery, which I think appeared on the archive in August or September of last year, and then there have been a couple of other papers as people sort of move up the food chain and in more complexity. This talk here and the work that I've done so far is much more narrowly focused. And instead of trying to do a whole analysis, I've been much more interested in the question of, can an LLM make a plot that would sort of pass muster? That is, it could give you some real information when you're in the middle of an analysis. I see that there are some chat messages coming in. If you've got a question for me, you'll need to interrupt since I'm full screen. I can't really see what those chat messages are without blocking part of the screen. So, can an LLM make a plot with just a simple English prompt? Not any overspecified, very complicated thing, not a JSON scaffolding, etc. Just a simple prompt. Okay, so when I first set out to do this, I thought we ought to do a couple of different questions to see whether or not it can make a plot. And so then, of course, the question is what plot should we make? And the obvious answer, being a part of IRIS-HEP and also have worked with Mason Prophet in the past, was to use a set of questions that we had developed to profile how well analysis description languages work. So these were developed in 2019, so it's pre-GPT-2. These were designed so that somebody could read them and understand exactly what was going to be required. They don't have a lot of context, but You could then implement them in things like RDF, in awkward, in nail, in coffee, etc. So the benchmark description is the question, and literally this was the text that got used, and then the motivation was just why it was we chose those particular questions as we were exploring in the space of analysis description languages. Okay, so what is the LLM going to have to think through? So here is question 6. For events with at least 3 jets, plot the PT of the trijet 4 momenta that has an invariant mass closest to the top mass in each event, and plot the maximum B tagging discriminant value among those jets in this trijet. So you're going to have to loop over all events, fetch the jets from the event if it has at least 3 jets, form all 3 pair combinations, pick the 3 pair combinations closest to the top mass, fill an appropriately defined histogram with the PT of that. Then, of those 3 jets that you just used to fill, fetch the B tagging discriminant and get the maximum one and fill the second histogram. And then, of course, once you've got the histograms, you've got to plot it. So these are the 2 plots that you kind of would expect. And well, given a particular data set, these are the 2 plots that should be coming out of an operation like that. But the point is can the LLM turn this English into this code that does steps 1 through 8? Okay, before we do that, we need to pick a technology stack, an implementation stack, how we're going to do it. We're not just going to give the LLM something open. So I chose ServiceX to fetch the data off the grid, awkward array and vector to manipulate columns, deal with four standard 4-vector algebra, invariant masses, etc., and boost histogram to make the plots. There's no reason you can't choose a second or any other workflow. I did a sec to see if this would generalize. I did a second workflow, which was prompt files for our data frame. I kept ServiceX, but the real reason for keeping ServiceX and not changing it in the second workflow is that it gives you quick access to data and is done by a web API, which is really conducive to just firing off a Python script and sitting there and waiting, because it's so much faster than running on the grid. So no reason you couldn't do the grid. It's just you need extra infrastructure to use the grid. Okay, so how does it work? So I have a bunch of separate hint text files. So a file that describes how you use ServiceX, awkward array, vector, hist, and we need something special, unfortunately, for the Atlas XAOD data, including phys-lite. That is not straightforward to use, especially when you are starting to do things like B tagging discriminants. Then a prompt, which kind of sets the stage, and I'll show you in a second what the prompt is. The thing about the hint text of the prompt is for every single question that's asked, they are identical. At the end, you append the actual question, and you feed that to a large language model, and you should get back, if all goes well, a Python script, which you can then run. The hint files you would change for different technology stacks. And the prompt you might change for different tasks. Say you wanted to extract machine learning data, training data, as opposed to a histogram or something like that. Okay, what do these hint files look like? They're just plain Markdown, frankly. So here's a formatted version of the awkward array and the XAOD data model. There's a GitHub up there where you can get a look at the hint files that are used. The first version of the hint files, I just used a large language model to draft them, turtles all the way down. However, even with working on the prompt, these still were too wordy. And the reason too wordy is important is because the more wordy, the longer the bigger your context that you have to, the bigger the text or the so-called context you have to feed the large language model. And it turns out large language models, even ones which have like a million tokens context, still do worse the more context you add to them. Furthermore, doing these shorter files really enabled cheaper models to run quite effectively. Some of them I also wrote by hand. For example, the XAOD data model, there really is no good public single source of documentation, and certainly not something that isn't behind a firewall that I was unwilling to work on enough to get an LLM access to. And then finally, one iterates. Those questions 1 through 8, I use them to adjust the markdown files in order to get to the point where the proper information was there. Okay, so here's what the prompt looks like, and so you can see it here. Uh, uh, Generate code, use service X to fetch the data, awkward array. So this is telling it the stack to use. Write the histogram files to PNG file, the histograms to PNG files. This is because the framework that's going to run and automate all this is going to look for the plots in that particular place. And it has some other basic things, and then it has the hints, and then the question, and then some final instructions here. And there's a prompt you can find in GitHub there. Sometimes you need to add a few things. Like, for example, there's some models fine-tuned to always create pull requests. Even when there's no Git anywhere discussed, they'll still try to create a pull request, which ends badly, as you can imagine, on a container that does not actually have Git installed. The other thing is that modern LLMs are fine-tuned to explain everything, and so you have to give it a place to explain, because if you don't, it will try to insert it in the middle of the code, and that often ends badly. Okay, so here's an example for plot 1. Plot the ET miss of all events. And so you can see the code, the Python code on there on the side, and you can see this very first part right here, where this is the query that actually goes and fetches the missing ET from the Atlas open data, divides it by 100 to get it to GV. Here's the data set name. So these questions have a data set name appended to them, so that the LLM is not trying to find a data set name. Here it actually runs service X, and then here it creates the histogram, fills it, and then saves it. Question 6, a lot more work. However, if you look at the code, it's pretty similar. There's some boilerplate to deal with B tagging that comes from some of those hint files, but it's generic. It's not tuned to this specific thing. And then here is all the actual work of the question, going through and creating those two plots. And amazingly enough, it does it, and you get the answer that you would expect. Okay, LLMs hallucinate or make errors, whatever you want to call it, all the time. So here's an example of a crash in service X. No data was returned. And this means, in this particular case, this is before we fix the error return in service X, but this particular case means that your data set name is very likely incorrect. So I had to use my expert knowledge looking at this, because I'm one of the people that works on service X, to know what was the problem. And then I added my expert knowledge to the hint files that were fed to the LLM, and now it could figure out what this particular error meant and where the likely place for it to concentrate its attention. And I only use that as a mild pun. So as you can tell, there must be a loop if it's trying to fix errors. So we take the final piece of software, takes the prompt, question and hit files, feeds it to an LLM, runs the code in Docker. If the code failed or didn't produce a plot, it goes around in a circle, and that circle goes up to 10 times. So for example, question 1, the OpenAI's 120 billion open source model took 6 tries in order to get it to the point where it took missing ET. So it can make progress. Though in general, if something's failed 3 times, it's likely going to go all the way to the max of 10, which I used. The other piece of the problem are hallucinations where it looks like it ran, it produces a plot, but the plot is incorrect. These are particularly noteworthy because you can imagine in a real situation running where you're actually using this, looking at a plot, and then the plot sort of looks right, but it turns out it's not. And so I'm really calling these things hallucinations. And to measure them, I know what the correct plot is looks like. I have some statistics for what all the correct plots should look like, and then I can compare them against each generated plot to understand when things go bad. All right, I want to run on lots of models to test this all out. So here's a list of the models I ran on. It's actually larger than this, but I eliminated a number of models which just weren't up to the task even mildly. So you can see they're ranked by cost. Most expensive is on the left, cheapest is on the right. This Llama 3.370 billion, that's all the way over on the right, is a very, very old model as these things go, and certainly not very capable, but it was one of the original open source models, so I kept it for that reason. Okay, let's look at these first 8 questions, which I used as training. What you're looking at here are every question was run 10 times, and then it had to produce, not only did it have to produce a plot, it also had to produce the right plot. So that would get you 100% if that happened. If you didn't get 100%, that means like 80% means 2 questions. There are 2 times that you produced either the wrong plot or couldn't produce a plot at all. You can't tell the difference between hallucinations and errors on this plot. And further, I'll just say that anything that's sort of on the left half will have a hallucination. The right half, especially this section of white right in here, are usually, it just fails to produce a plot at all for most of the time. So you can see here, GPT-5 Mini, a relatively cheap model, is kind of punching a bunch above its weight. Some of the more expensive models are struggling, and it turns out the reason the more expensive models are struggling is because they start making assumptions that go beyond the question. So, for example, Claude Opus would often, oh, the person is probably interested in another plot, so it would make an extra plot, but then it would crash making that extra plot, struggle to get that right, and then somehow mess up the original plot in the process of trying to fix that up. Okay, now, so I kind of trained the hint files on those. Need to run on some questions that weren't done in the training. So I don't have the list of questions here, but these were come up independently, even of me, David Lang, Peter Elmer, and Ruta, a summer student that we worked with, came up with a series of these questions. And so you can see what this looks like. And clearly, it does not do nearly as well. That said, the questions aren't carefully curated exactly the same way as they were before. Question 16 is particularly interesting, and notice that things don't do very well at all, but we'll come back to that. So here is the question, if you want to talk about cost versus the success rate. So along the bottom is exactly what we saw in the other plots, and then across the top is, across on the y-axis is the cost in cents per successful run. So Claude Opus 4.6 is just below 20 cents in order to, on average, to answer those 8 questions. It's cheaper for question 1 than it is for question 8, but this is just the average. The GitHub repository contains this plot per question if you wanted to go look. You can see there are a couple of open source models down in here, like Kimi 2.5 and a GLM 5, for example, but mostly this 80% and above is occupied by the larger and proprietary models, unfortunately. Here's 9 through 15, and here you see really the only ones that make it above the 80% are going to be some of these larger frontier level models. You can also see I have a cutoff at 5.2, and we're already at 5.5 for OpenAI and Claude Opus 4.7. This field moves so fast. This is a kind of interesting one because there is so much left unsaid in this prompt. So let's say you have a z prime to TT bar, and I want to reconstruct that z prime in a z prime to TT bar 3TV data set. So this was suggested by Alex Held as a possible question. We ran it. This was like in August, I think, and he looked at the code, and as he put it, it wasn't unreasonable. It wasn't leading cutting edge, but it did do the right thing. It used the WMAS constraint to choose the smaller PZ in the jets, for example. It was interesting is that the big models like GPT-5 at the time made coding errors that it had never made in other questions, which begs the question, are you getting to the limit of what these can do? This is too simple or too much of a prompt. It requires too much effort on the part of the model. I suspect in 5.5 or 4.7, Opus 4.7, you probably wouldn't have this problem. You'll just hit it later on with a more sophisticated thing. Okay, so let's move on to some larger questions, which accidentally feed into some of the talks that are about to give. So what data set should we use? So for number 6, question 6, this is the actual text that was handed to the LLM. So you'll see it has the in Ruscio data set here. And why can't I just say semi-leptonic TT bar? I mean, that's what I mean here. Why can't I just use that? So every experiment has a wealth of metadata associated with its Monte Carlo and its data sets. Twiki pages, at least in the Atlas experiment, often maintain which samples are used for what. And so imagine, furthermore, sorting between run 2 and run 3 version of the analysis. This in semi-leptonic TT bar will mean very different things in these two runs. And then there's also questions of full simulation or fast simulation. And then you've got to get the production cross sections and efficiencies if you want to scale those plots correctly, which those plots earlier on were scaled by those numbers, by the way. I forgot to mention that. That said, there are rules and there are even experiment scripts. And so the question is, how hard is it to write a tool that would use it? And to first order, it turns out that's not that hard. I had a whack at it, but I think Jordan and others have done a much more sophisticated version than what I've done. But you can kind of see the way to the end for being able to specify something like this. And the reason this is important is, let's say you have a paper and you're reading somebody's paper, they do an analysis, they're not going to specify what data set was in that paper, or maybe it's irrelevant because it's from a different experiment. You're going to need to have some help to look this stuff up, or it would be nice to have some help to look this stuff up. So what might be next? What should we be writing? Should we be writing tools or MCP based, that are MCP based? Should we write prompts that are used to accomplish these tools? Should we, I think in the end, we should shy away from writing these big, complicated, integrated systems. I think the tools, prompts, and hint files are going to be reusable by any system. Even humans can use some of these systems. A summer student was using some of these prompt files to figure out how to actually write the code themselves, for example. IDEs sometimes have infrastructure attached to them, like VS Code. It would be nice to be able to use it there as well as from, say, a command line. In short, we should be building Lego blocks, not buildings, I think. And we need a HEP repository of tools served on the web or at a GitHub, somewhere publicly accessible. And we are going to have to address some tricky things, like, for example, accessing anything in an experiment requires requires some sort of authentication, because we don't just let anybody into our experiment data. Another question is a huge amount of engineering time, I use that in loose quotes because it was me writing it, went into writing this code for some of this testing before. It's all a custom framework. It uses directly OpenAI's API with a backend of OpenAI or OpenRouter or others to actually run the models. But is that really where we should be spending our time? And my conclusion since doing this work is no, we should not. We should be instead using the frameworks that have been developed by many people. So there's open code, there's Claude code, there's Codex, um, and then they all have extensibility at this point. So you can add a plugin. So there is in this link up here, you can go see an IRIS-HEP repository for a plugin, which allows you to write a question that looks a lot like this. So plot the ET-miss of all events, so you'll recognize this is question one. And lo and behold, that is the output from Codex. This I also tested it in Claude Code. You get a histogram. You get the correct histogram that looks like this. And if you look carefully here, you'll realize even cooler, it's produced a standalone Python program, which you can use a tool like UV Run. So it's got the PEP, whatever, I can't remember the number for the PEP here specification that lists its dependencies. So this is, all this was is reformatting those hint files I had before. I didn't add any new information. And this is my point about the really interesting part of this work is generating those hint files or those context files. Then you have to deal with the format that they go in order to feed the particular system you're using, but you only have to do that hard work once. So I just like to say, no, I think we should be dropping our own code that accesses LLMs directly. So what are next steps? Well, I think it's pretty evident. It's easy for one person to get going. I'm a prof. I have to teach. And I've got students and postdocs, etc. If I can do this, probably just about anybody can do this. And I think given those papers that are out there, we've achieved the level of proof that this is useful. We've passed that. The second question is, I think that's one conclusion. Next is, what about working at scale? Move away from these smaller contrived demonstrations. Use 100 terabyte data sets, modern analysis facilities, at scale questions and analysis, and perhaps the complexity of a full analysis. Imagine having to deal with the context, the LLM type context, over a full range of experiment-specific tools, facilities, and best practices to produce an analysis that was, review worthy, internal review worthy. And what would the cost be? And especially the cost compared to people, which is the only reason we're sitting here talking, is that I think a number of us think this will be cheaper and thus enable people to do much more than they are now. So building an ecosystem of skills, of tools, and I think we're going to need to do some engineering of context. Like, how do you steer an analysis over weeks worth of work? From my point of view, specific goals, besides trying to get the previous work out in a paper form so I can at least refer to it because it's already woefully outdated because I've just taken too long. On the open data, obviously the AGC from the IRIS-HEP perspective, and develop a prompt which is loose enough to specify or tight enough to specify the analysis, but nothing else. Use the context, run it 10 times. How different are the answers? What's the cost? Exploring things like that. And then within Atlas, I really want to repeat a non-standard final state analysis. This is because this is what I'm mostly interested in, so I know most about it. But it'd be very similar to above, but unlike the canned analysis, maybe target run 3 instead of the run 2 one that we're repeating. Okay, so then I have my conclusion slide, which I basically repeat what I just said before, so I will just stop right there.
Okay, thanks very much.
Yeah, went longer than I intended, sorry.
No, that's okay. The concern about time is more about on your end than ours, so I think this is okay. But yeah, thanks very much, Gordon. And I think I'm probably not guessing too much to say that we're getting hints of some of the things that you might be showing off at CHEP as well. So I think people should probably keep an eye out for Gordon's talks. So we have time for, I think, probably 1 or 2 questions, as long as Gordon can hang on. So let's go, Jordan.
Yep, go
Jordan start, because he's got his hand raised on Zoom.
Hi, Gordon. We'll probably talk offline at some point, but can you go to slides 13? I've seen this before, but maybe you're gonna have to explain. What is this a command? Or is this a copy paste prompt that you do? Or what is this?
Okay, let me make sure I'm unmuted. Okay, so the way this works is I don't ever type anything myself. This is all completely automated, and I directly am using the API here. So a Python script takes this prompt, and you'll notice these curly brackets in here for hints and question. Those effectively are Jinja 2 template, if you want to get technical. This is a Python library for doing text templating. So it fills the templating, fills that in. Those hints are loaded. Which hints are loaded is guided by a YAML file, which you can find in the same GitHub where this simple prompt link is. And it builds this long text, just ASCII text. And then it just takes the text and it just does the API call, and then it gets back something from the API, and it's supposed to be in this format under final instructions. It expects it in that format and it extracts the code from that. So does that answer
Okay,
the question you had?
yeah, this is, you're basically generating the harness. Okay, this is fine. I am just thinking about it more generally. One could imagine that you have a command, like for example in Claude, you can have a slash command, or having some sort of sub-agent that is designed with this personality. Because I'm just thinking about taking the work that you have and trying to kind of stick it into Codex or Claude or Copilot in
Here,
kind of a reusable way. And
this
I
is how you do
imagine
it.
them, yeah.
This is right. Look at the slide 28 here. So that is Codex right there. And you'll notice the little chevron. Hopefully you can see my mouse right here. That dollar sign invokes a particular plugin or skill. And so that is just telling Codex, hey, these are what are going to be relevant. And then the instructions follow. And so, I've replaced that huge prompt with just write a standalone Python file that we can use with UV run to force it to look at a particular skill, which tells it how to write those PEP, I can't remember the number, sorry, files that will do the following, and then blah. And that there is a list of skills which are made out of those hint files. So I think this is exactly what you're talking about. And if you're curious to look at them, there's this link up here, plugin. Click on that, and that will go to a imaginatively named IRIS-HEP Git repository called Marketplace. Sorry about the name. But at any rate, you can then install that in either Claude Code or Codex, and you should be able to just type this and it should do the right thing.
Right. Yeah, you're just referencing the plugin. Got it. Okay, this is just Codex does this a little differently, which is a little bit annoying. But for example, one issue, we can talk about this later, but one issue with the way Codex does plugins is it puts too much in the context, as opposed to what Copilot and Claude does, which is where they load the plugins and the available tools,
Yeah.
but not
So
everything within the plugin.
yeah, so
Codex has a slight problem.
we're getting a little technical, and I think one of the biggest problems that's unsolved is, to actually do the analysis because of the data sizes, you're going to be running to run over days or weeks. And the LM is going to have to keep cutting in and out. And as you and I have both mentioned in numerous different meetings, context is king. You want to keep it small, neat, and only the relevant information. And so that's definitely something that's going to have to be addressed. And I think, I don't actually know much about the implementation for code and Codex behind the scenes, and what they put in the context. But even if it's very efficient in code, you eventually are going to have to deal with this problem. And everything now does subagents. So that isn't, that's an obvious way to help you deal with the context. But all of that we're going to have to figure out. And part of the reason I say this word of context down here is, not only that, but we're going to have to figure out how to put all the running metadata, like what's being done, what's next, etc. We're going to have a layout in your Git repository, so when the agents come back, they can look at it. Maybe we should be using issues in GitLab and GitHub to control the age. I don't know how this should work, but all of that work is going to we have to come up with something in order to steer the analysis, especially for anything that's complicated and is going to need a human in the loop as we go. Maybe the human's not writing the code, but they're definitely going to be help making physics decisions. So yeah, I totally agree, Jordan. I don't have an answer. I think you and I both probably have ideas of how to start, and then we see what doesn't work, and and hopefully we change our approach.
Okay, we should probably move on given time, but thanks very much, Gordon. I think this was an excellent first talk to kind of kick this off, and I also think we could probably use some stickers that say "context is king." I think that would be some good mantras for us to internalize.
And if anybody has, this is not a draft of the CHEP talk. This is like a parallel. This is closer to the parallel talk I have to give. But if anybody has ideas of what I should be including in this talk or the plenary, which is meant to be much broader and include lots of people's work, not just mine, feel free to send me, because I have ideas, but I'm desperate always for more ideas.
Sounds good. All right. Thanks very much. We'll let you go teach.
No, I have time.
Oh, okay.
I will stay here a little longer. I think I teach in a little less than an hour. So.
Oh, okay. Very good. All right. We'll move on to Mohammed then. And okay, excellent. You've already got your slides up. Thanks very much, and we'll let you take it away.
Okay, thank you, Mattia. Thank you for organizing that topical meeting. So, good afternoon or evening, depending on where are you joining. So today I will be talking about something I have been building quietly alongside my analysis and BV Finder work, which is a small ecosystem of tools that tries to make AI assistants and LLMs genuinely useful for any kind of daily work that particle physicists actually do. Not useful in the sense of ask it a question and it gives a plausible answer. It's useful in the sense of it can open your root files, read your branches, make a plot, find the relevant code in GitLab, for example, and pull the right references from INSPIRE-HEP, all in a single coherent workflow. So the talk has 3 projects at its center. There is root MCP, 7 GitLab MCP, and INSPIRE-HEP MCP. I will explain what they are, why I built them the way I did, and where I think IRIS-HEP is positioned to help standardize this kind of infrastructure and share ideas about this. Just a second. Okay, so before anything else, let me define 3 terms that I will be using throughout the talk, because people in this community might have different levels of familiarity with the AI tooling landscape that we have. The first thing is MCP, or it stands for Model Context Protocol. This is an open standard originally developed by Anthropic. It's the company behind Claude models that gives large language models a structured way of calling external tools. Think of it as a clean JSON interface between the model and the outside world. Be that a file system, a database, or an API, the model can discover these available tools, call them with the typed arguments, and receive structured results back. The second concept is CLI, which is many people will be familiar with that. It stands for command line interface. Nothing exotic here actually, but in this context, it's just a shell tool that exposes the same functionality, the tools, as the MCP server, but you drive it directly from the terminal, which is useful for scripting, testing, understanding what the tool actually does before you let it you let your agent actually near it, or you can reproduce. It's easier to reproduce what the agent does with a CLI than MCP. I will talk about the difference, what the difference between them in a little bit. Skill.md, this is just a one that perhaps least familiar. A skill file is just a small markdown document that teaches an LLM agent what commands exist, what their arguments are, and how to compose them. So no server process, no JSON overhead, just a description file that sits alongside you as your CLI tool. The model reads it as part of its context and knows what it can do. I know that skill means a lot more than what I mean, but basically this is what I mean by skill in this context. So just subset of skill, meaning what I'm going to use. So these three things, MCP server, CLI, and skill file, all share the same underlying backend in the tools I will show you. That shared backend design is a deliberate choice, and I will come back to why. Okay, here's what the next couple of minutes will look like. I will start with the motivation. Why does agentic AI actually matter for our HEP overview workflows? Beyond the general excitement about the large language model, then I will walk through what MCP solved for early LLM tooling and why I have been increasingly interested in pairing it with lighter skill plus CLI interfaces as a replacement of MCPs. After that, I will go through each of the three projects with a concrete example just to give you an overview of what they are doing. Then we will look into how these compose into a single end-to-end workflow that can be used and what the deployment patterns that make sense and in the context and in our different contexts, or maybe IRIS-HEP is interested in like standardized. Then I will close with open problems and what I would most want to see this community engage with, from my opinion, and just have a discussion. So let's start with the question that's easy to ask but easy to answer wrongly. What actually hard about AI for physics analysis, for example? The usual answer is that the model doesn't know enough physics. In my experience, that's rarely the bottleneck, although it helps in it sometimes. But the real problem is access. As a large language model by default lives in a context window. It has no idea what's your root file. It cannot look at your Git repository. It has not read the paper your colleague submitted that might be related to your analysis. When you paste code in the chat and ask it to help, it's helping you with the text you gave it, not the actual analysis infrastructure you work on every day. Even with agents, agent has limited access, and sometimes they will go into a loops trying to access the files or like use the tools that is the standard Unix tools, for example. The traditional loops looks like this. You describe a problem, the model suggests a script, you copy it out, or it tries if you are using an agent, run it, edit it, run it, debug it, and so on. And if something breaks, it starts over or like do some iteration. And each iteration crosses some gap between the model and the real environment. What agentic loop changes is exactly the gap. The agent can perceive, read files, query API, search code. It can reason over what it finds and plan multi-step actions. Not always correct, but it can. But the thing is, it can act, it can call tools, it can run commands, compose results, and it can report back in some structured, useful form that for a human to see. The key idea is, and I want to be direct about this, is that useful scientific assistant is not a smarter model, it's a thin orchestration layer over domain tools that already exist. RootEdge already works, GitLab already works, InspireHEP already works, other things already works that can do, but I will be restricted to these three things. The question here is whether an agent can use them effectively or not. So MCP and why it mattered. So when I started this project, the main problem was that every integration was bespoke. You would write a wrapper for root, another one for GitLab, another one for literature API, and none of them could talk to each other in any standard way. MCP, which is new, I think this came in December 2024, solved this exactly. It gave us the common vocabulary. Tools have names, typed input, typed output. An LLM client that speaks MCP can discover what tools are available, call them directly and correctly most of the time, and interpret the results regardless of what the underlying backend is actually as. So for our field, high-energy physics specifically, this matters because our infrastructure is usually diverse. It's really diverse actually, and often institution specific, experiment specific too. CERN runs its own GitLab, for example. We use Root, which is not part of any standard AI tool chain, and it's weird for most of the programmers actually. Inspire Hub has its own API. MCP gave us a clean way to run each of these as tools that an agent can call without requiring custom integration each time. The diagram is on the right shows the basic topology. The physicist talks to an LLM host or like LLM agent, for example, tool, which talk to an MCP client, which talk to individual MCP servers, one per domain, for example, root MCP for data, CERN GitLab MCP if you are looking for code, for example, and each server sits in front of the actual files or the API that we are calling, in case, for example, of CERN GitLab MCP. Now, after using these tools in real analysis work for several months, I developed a more nuanced view. MCP is excellent for certain things: remote services, strict validation, autonomous agents, multi-user deployment, which is very important if we want to deploy this outside of your local machines for access control of the root files, for example, because this is data that belong to the experiments. But for a lot of the daily analysis stuff to actually do, the overhead is often more than I need. So every tool call carries a JSON payload. The full tool catalog stays loaded in the model context all the time. When something breaks, there are several layers to step through before we understand actually what went wrong. But the alternative is the scale plus CLI pattern, which trades off some of these formulas for simplicity. So we have a single markdown file that describes what a CLI tool can do and what we actually want it to do. You point at the agent at it, and it drives that command line directly. Outputs are plain text. Shell composition works naturally. In this case, the context footprint is much smaller. And some of my tests, it's up to like half smaller for the part about like the MCP and CLI. My current position is these are not competitors, they are layers. MCP is the right choice for remote surfaces, strict schemas, and true multi-agent autonomy. But Skill plus CLI is the right choice for analyst workflows on local data where token efficiency, because this means money most of the time, and debuggability matters. Concretely, the design I'm converging on is one shared backend, two front ends, one scale description. That's what all the three projects now follow. Let's now go about like introduce the three projects and talk briefly about them before I go into details about each one. So RedMCP is a root-aware interface for file inspection, branch reading, histogram computation, selections, and plotting, and many other things. It has both an MCP server and companion CLI called Root CLI. It's focused on local analysis workflows. For the CLI, Root MCP can be deployed for multi-user. Actually, most of the work is basically working around authentication and CERN stuff, which is I'm going to talk about in a minute. CERN GitLab MCP and CERN GitLab MCP is just a name. It would work with any GitLab instance. Why it's called CERN is just historical reason. So it's a GitLab aware interface with many MCP tools covering project search, file retrieval, code search, and experiment stack discovery, at least for LHCP. It might be extended to like Atlas and the other experiments if people want and actually would help with this. So it supports both Studio and HTTP transport modes, which means that it can be deployed in multi for multi user in an easier way. All of them actually can be, which matters for the shared deployment, of course. And it also has the CLI and skill file to help replacing it for like the lighter workflows. And we have INSPIRE-HEP, which is the literature-aware interface for searching papers, transferring citation graphs, and fetching metadata from INSPIRE-HEP API, DOI, or archive identifiers. And also it helps if you want to generate web text out of the thing. So the focus on these tools is read operation more than the GitLab official MCP. It's paid, but also it's more focused on like actually letting the agent write to GitLab instead of like reading from it. So the philosophy across the three is the same. We expose existing high energy physics infrastructure through the interfaces that the agent can actually use. So every project ships with documentation and extension guide, so that collaborators can add new tools without understanding the whole stack. I would welcome any contributions. Um, but also there is a guide on how to use it with all the common tools like Cloud Code, Codex, and all these things. Let me make this concrete with root MCP. Suppose you have a root file from some B decaying to GPSI K analysis, and you want to first look about the GPSI mass distribution. Normally, you open a Python session or write small root macro, figure out the tree names, list the branches, make the histogram, apply selections, set the campus, and so on. Or you can let your agent discover this by writing the same code, try to fix it if it's not wrong, and so on. With root MCP, the workflows becomes you tell the agent what you want in plain language, plot the GPSI mass from the G2PSI truth file, for example, and it handles the mechanics. It reads the file structure. It will use the correct tool from root MCP, which will do it. So LLM doesn't try the code itself. It just uses the tool itself directly. It identifies the relevant branch. It computes the histogram that you asked. Run, for example, a thread that custom proof thread and saves what for you to show. So the output you see in the slide is represented. What actually comes back means RMS thread parameters with uncertainties. The agent is acting as thin wrapper over the pi root in this case, or a root uproot, which is doing the actual work. One update worth mentioning is that I presented the root MCP to the root team earlier this year, like almost 2 months ago, and there is ongoing conversation about deeper C++ integration, and actually they are not very interested in Uproot as a backend. But anyway, that's beside the point. But these things would allow us to open things like T3 Draw on the MCP side, which is going to be a meaningful extension. So people can now have like both of two words, C++ and Python. Seven GitLab MCP is perhaps the one that has been seen most of the real world use because it presented to many people. Also, because the software archaeology is something that every collaborator does constantly, so I would think that this would be useful for many people. Or not. You need to find, for example, analysis example. You need to check how someone implemented selection and more. More is the trigger software for LHCb. You might need to understand the CI configuration in the repo you have never opened. All of that currently involves browsing GitLab manually or like trying to ask someone. That's also a valid thing. But these things are solved and doesn't compose with anything. The prompt on the slide, so for example, search for RUFET usage and LHC more, produce exactly what you would want: file paths, line level matches, and project metadata. The same query from the CLI looks identical, which is the point. The HTTP transport mode is in the new version is what makes shared deployment practical. Multiple users can hit the same server instance with a central authentication and audit layer sitting in the front. And I will come back to that in the deployment slide. Okay, the third one is the INSPIRE-HEP MCP, and the motivation for it is slightly different from the other two. So Root and GitLab are workflow tools. INSPIRE-HEP is more about literature, and you might reasonably ask whether a literature search is already solved by general purpose AI. The answer is not. For HEP specific metadata, finding paper by collaboration, transferring citation graph, or generating correct text from INSPIRE record ID will require structured access to the INSPIRE API, not just a web search. The example on the side shows a query for 2026 LHCP paper on vertexing. The response returns some paper metadata archive ID and ready to paste entry. If you ever spend 20 minutes reformatting a reference by hand, you understand why this matters. The deeper point is that analysts navigate data, code, and literature as part of the same workflow. An agent stack that only covers two of those three is incomplete, at least in my opinion. Okay. So now let me put all three together because the individual tools are less interesting than their composition. So imagine an agent working in a new analysis channel. It starts by searching GitLab for prior analyses, existing selections, restructure algorithms, helper scripts. That's GitLab CERN GitLab CPA. It then opens the Monte Carlo sample that you have and produce the first efficiency plot. That's root MCP. It finds the two or three foundational papers that define the signal. Model generates it text for your analysis node, for example, later, and annotates the output that inspire HEP MCP. The final artifact is a short report with plots, code references, and bibliography assembled without analysts ever manually switching between contexts. All that's an ideal case. Well, of course, there will be problems and you will iterate, but that's part of it. But the idea is that this is not science fiction. Each of these steps works individually today. The orchestration layer to change them is what's still being developed. And that is the area where IRIS-HEP could genuinely help by defining the composition interface for all these things, which, as people suggest, like Dr. Gordon suggests, that might be some marketplace or like some tool that can we can organize it in a more better way. In a better way, sorry. Okay. So let me be direct about the trade-offs between MCP versus the Scale plus CLI that was, because I don't want to oversell either approach. So MC gives us strict schemas, validates input and output, interoperability across any LLM client that speaks the MCP protocol, and it has native support for remote multi-user surfaces. The cost is, of course, the JSON overhead on every call, the full tool catalog loaded into context, and the more configuration layers to debug when something breaks, which is annoying. Skill plus CLI gives you tiny context footprint, just one markdown file, direct shell output you can inspect immediately, natural composition with pipe and redirects and shell, and significantly lower token overhead for any routine tasks that you are doing. The cost is no schema enforcement, tighter coupling to the specific CLI tool that you wrote, and less portability across different AI clients. And you are adding variation on like how well is going the model is going to use your CLI. So the design direction I'm moving forward isn't don't choose, build, share, backend, expose it as both empty MCP server and the CLI, and ship skip a skill file alongside. Use MCP for autonomous agents and remote services, and use skill plus CLI for the analysis workflows where simplicity and debuggability matters more than being formal or like being strict. Okay, so on deployment, there are two sensible patterns, and these suit different scales. Pattern A is a local researcher lab setup, so a laptop or workstation, like PC, a local MCP client or CLI enabled agent, which has direct access to local files and private repos. This is the lowest overhead way to start, and this is what most individual users will reach for first, of course. Pattern B is a shared surface, HTTP backed MCP instance that serves many users with central authentication layer, quotas, and audit logging if there is like some. It's expensive to run these things, especially if you have also the model access provided by some central things like CERN, for example, or like your experiment. So this is the model that makes sense at the collaboration level. I will mention concrete success case here. So the CERN ML service has agreed to host these projects and cover the API costs for the development because they are hosting and providing some support for people working on AI projects. That's the transition from some personal, and also it's focused on like providing these tools on a collaboration or like certain levels. So we are still working on the infrastructure thing aspect. So but the idea is that that's the transition from personal tool to shared infrastructure and requires very little change to architecture, which validates the shared backend design that I'm talking about, because you can work it in the two patterns, like the local one or the shared one. So I think the IRIS-HEP here opportunity is to go a step further and define the standards, or like the way that we would put all these things, so that would let any experiment deploy a compatible agent stack without starting from the scratch each time. So something like infrastructure that we can put this into tools, like the marketplace for skills for other tools, maybe even other MCP servers. This is what I have in mind by this. So, so let me be specific about where the community input. I think where's the community input would matter most is interfaces. So, for example, when should a tool expose MCP, CLI, or both? What belongs in a skill file versus some strict JSON schema? There is no consensus yet, I think, because this might be a trial and error regime. So evaluation, how do we measure actually whether these tools actually help? Antidote demos are easy to produce, rigorous validation, analysis, time saved, for example, onboarding speed for new people, correctness rates versus like you just using the agents without these tools, reproducibility, which is very important, and it's much harder and requires community level agreement on what success actually looks like. And also the shared backend. So some integrations should be built once through file access, for example, some GitLab integration, Inspire, HEP search, and these things. Maybe even something for plotting. We're using scikit, like packages. That's very useful. So if every group rebuilds these independently, we accumulate fragmentation. So IRIS-HEP might work on these things. So like we can have something that would work for experiments, maybe not out of the box, but closer to this. Also, we can like talk about like specifically with certain people and like experiments like authentication, the quotas, and audit logging, because this might be needed if we want to like say, okay, who accesses the data of like whom and like responsibility. Um, so these are some of the questions that will determine whether this stays a research prototype or becomes a real collaboration tools. And reproducibility, of course. So, for example, the idea is, can the agent leave an explicit record of what it did, with which commands it ran, which files it reads, which plot it produced, and who actually who did this, and which references it fetched. The trail is probably going to be an essential for scientific credibility or reproducibility and overall. Okay. There are some lessons from this work. Four things that held well from the original design. So that domain-specific tools consistently outperform generic chat or generic agent for these tasks. Shared backends with multiple front-end scale in a way that a single interface tools don't. Connecting literature, code, and data in one stack is genuinely more useful than any of the three in isolation. Or you like asking ChatGPT, for example, like asking the chatbot something and letting the agent work with root MCP directly is not as useful as providing the tool for the agent. And in practice, analysts prefer direct CLI workflows for anything they do repeatedly. For the very few people that I worked with directly, including me. So, but there are things that are still open. So, compact structure output is harder than it looks. The model needs enough context to reason, but not so much that every call is expensive. The autonomy versus safety balance for tools that can write to GitLab or like modify analysis pipeline and is unresolved. So also evaluation beyond demos is absent. and packaging these for deployment at collaboration scale is not yet solved. The working conclusion I have arrived is that the winning abstraction is a stack, existing APIs and libraries underneath, CLIs and MCP servers on top. Scale files are the lightweight instruction layer that ties it together. So, and to summarize and close, is the strategy as we treat the data, code, and papers as first-class tool services. For agents, use layered access models like MCP server, CLI, and scale files built on shared backends so that any front end works without duplicating logic and without the end user actually having to worry about all of these things. So the ecosystem is already forming. The root team is collaborating on deeper C++ integration. CERN ML Surface is hosting and supporting these tools. IRIS-HEP is a natural place to move from individual project to shared infrastructure. And yeah, thank you for listening.
All right, thanks very much. This is a really nice overview of all of this work. So we have hands raised from a few people. I think I saw Jordan's first, so let's go in order. Let's go Jordan and then Gordon, and then yeah, if anyone else has, okay, I see a few more. So yeah, go ahead, Jordan.
Hi, yeah, this is a good talk. I wanted to ask about the CERN GitLab MCP. I guess you are probably aware GitLab itself ships an MCP server with every GitLab instance and it's up to whoever manages the instance to enable it. Have you already tried talking with the CERN team to see if they would enable their GitLab MCP server or
Uh,
not?
yes, I have talked with them, and they are not going to do it because it's paid. And not only it's paid over something like a GitLab do, so you and it's paying paid. You have to pay it per user. So I think it's very expensive for them. At least this is what I hear them
No,
talk.
it's a feature flag. I think they might be confusing this with the usage of like GitLab Duo. GitLab Duo is a per user cost, but enabling the feature flag to have the GitLab MCP server is just a flag. They already have it in their
Uh,
instance, and they just need to enable it. In which case,
I
you don't necessarily need a separate certain GitLab MCP.
Okay, it might be, but I think I have to tell them, and there was a reason. This was the reason that I was given. I'm not sure. Maybe because also it can be a flag to be used, but the license doesn't allow you unless you are having do. I don't know about the details, but I have been working with certain IT on these things. So
Okay.
Okay.
they might be wrong too.
Yeah, it seems like this is something that there can be some offline follow up on. That sounds definitely of interest. Okay, Gordon, let's go to you next.
Sorry, I accidentally brought up right on the screen tools and then I couldn't unmute. Okay, so let's see. Jordan asked actually one of the questions I had, which was about the GitLab MCP. I guess I'm curious a little bit more about how you decide between the CLI and MCP split. Um, here's my thinking. For many of us in the experiment, they have a very specific setup in which you can run the CLI command. So you've got to be using Alma 9 as a Linux base. It's got to have CVMFS installed. You've got to do, I'm talking about Atlas, of course, here because it's what I know. You've got to do the software setup, and then you have to set up um, a particular package, and then from there, sometimes you even have to select another version below that before you can even issue a command. So this means to me, if you're going to use CLI for those kinds of things, you're going to end up having to have some, like a pretty specific um, local platform. This feels to me like a place where MCP makes more sense because then you have a remote server. The remote server can be specifically configured to deal with a particular CLI that you want to use and turn that into an MCP. So I guess I just wanted to know a little bit more about how you envision this CLI versus MCP. Uh, you mentioned remote servers and things like that, which are great, but I guess I get a little worried that this means you'll have to have a particular and very specific software stack locally, if you're not careful about where this division occurs.
I mean, not to talk about CLI versus MCP for all the tools. If we are talking about these three tools, for example, in particular, we don't need like to have very specific setup for them because like they are Python packages at the end of the day, and they will be running the root CLI, for example, and root MCP is having the same tools, will do the same things. So just the commands, if you have access to the CL, like access to the shell, which you would have, of course,
You
then you
access
can
to the
run
which? Sorry, I didn't get the word you.
to a shell, to a shell.
Oh,
Like the
shell,
agent can
shell.
access,
Yeah, 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 yeah. Yeah,
run things in a shell.
shell feels pretty universal. That doesn't feel like a big ask, but even root can be an ask because you've got ecosystems out there under x86 and ARM, et cetera, et cetera. So you can quickly run into trouble even for something as simple as simple. I put in huge air quotes as root.
Root is not simple, but yeah, I understand your point because there is a dependency on root. So this assumes actually part of the setup for root MCP, the configuration is that you would need to have. So for example, if you are using root, not uproot. So uproot is dependency, so it installs with root MCP.
Right,
But if you
right,
want to enable the root so that you can access something like data frame or like run C++ macros, then you
right.
will need dependency on root. And you have to
Yep.
set up this in your environment. Yes,
Okay.
so I agree. It
All
would
right.
be painful. So something like MCP, remote MCP server, when actually the tool calls are happening on the server, not on your local machine that you are using, even if it's LX Plus in this case would be more suitable. So yeah,
Yep.
I agree.
Okay, cool. I also look at this sometimes from my point of view of mostly using Windows, which is great from the point of view of making sure that you could install and run this from everywhere, because obviously Windows looks very different from any of the Linux shells. Okay, so the other thing is this Inspire HEP MCP is awesome. I'm totally going to start using that. On slide 13, you mentioned something about the CERN LLMs. I was wondering if you'd use them for any tests. So I couldn't tell if you'd done any testing here other than sort of anecdotal testing. But my impression the last time I looked in on what CERN was doing was those models were too small to do anything really sophisticated, that they had available for obvious reasons and good ones.
I mean, now at least I don't know, but when in time you were thinking about, but at least for now, they have like subscription to many of the good models, proprietary
Okay.
like
Okay.
models.
Yep.
So I'm trying with many models.
Yep.
They even self-host like Quinn and Mistral and these things.
Okay.
They
Good.
have a good models
Yeah.
and bad models actually.
Yeah. They had a at least one. Last time I checked, the subscription wasn't available. They just had the open source models, but all the open source models were fairly small. I think they had one that was like 100 billion or something, but even 100 billion is not good enough I think, for what we need to do. And then last question was slide 14. You mentioned reproducibility and agents leaving an explicit trail. So I wanted to get your thoughts on, should an LLM have any role in making the final plot for, let's say, a paper, or final cross section extraction or whatever, or that is, you say, I want the final plot, and the LLM goes and generates the final plot. Or should the LLM be writing the code, which you can then run from a command line with no LLM involvement to generate the final paper or the final plots or numbers? I was just wondering where you fell in that along that range and your reasons for where you sit.
My point is, because if it tries the code and you run it, of course, assuming it's a correct run after some couple of iteration, that's very different because this is not this is just you. It gives you a code and you run it. The thing is, for agent, for my workflow, for my what I'm thinking is like, okay, it will run, create the plot using tools, or even if it generates the code that runs it, and then it looks into the code, assuming it has vision capabilities, and can reason about it. I'm like, okay, this seems reasonable for some reason or not. So I'm talking about the second part, which is like, okay, it gave you the plot, it does run it, and then it says for some reason this is the plot. I think it's good or not, depends on something like this. So this is
Okay.
my point is
So
this is
yeah,
what I
so
mean.
maybe there are two different situations here. One is where you know, okay, I'm trying to explore. There's this weird bump. Let's start slicing and dicing the data to see if we can find out if the weird bump is coming from some piece of fiducial space or something like that. Um, and there, the LLM will help you make the plot, and if it's not all 100% reproducible, that's fine. But if you're talking about something that's going to go for publication or review, I guess for me, an LLM, because there's an inherent random number injected in there, should not be any part of the process. It should write the code. I'm totally comfortable with that. But every time I run it, I need to get exactly the same thing. And for me, that means no LLM is actually involved. Um, maybe the LLM fires off a snake make or something, but it doesn't. Once the snake make is up and running, no LLM is involved. So I guess that was the difference I was trying to tease apart. And it sounds like you're mostly concerned right now with, you know, okay, let's do a deep dive on this plot and understand where these features are coming from, which
Yes.
is
So I
totally
just want
different.
to clarify something because in root MCP, for example, root MCP, if the LLM, if the agent is using the root MCP, it's using already functions. These functions does some operations like, for example, fit using some model. My point is, it doesn't give you the code like code that will run this. It will use the already built-in code and the root MCP. The point is, how would we make sure that it leaves a trail so that okay, we know how the agent created this block using like okay, I applied some cuts before doing the fit. What are those cuts and what the fit was using parameter? Does it fix some like the sigma or not? And these all these decisions, we want to leave a trail because if it has the code that was produced, this code, like for example, using uproot and using scipy and whatever it uses, then we can say, okay, we can look into the code that it ran and then we will understand how the
Right.
plot is created.
The way I think about this is if these plots are going to end up in the note that goes before the review board, and then the review board says, um, "Did you remember to apply to cut out the transition region between the barrel and forward calorimeters?" You need to be able to go and find some code, even though you made this, this plot you wrote the code to generate the plot like a year ago or whatever. You need to be able to go and find that code and say, uh, yes, I absolutely did cut out that transition region, right?
Mhm.
And this is what I mean by reproducibility or you've got a new version of the Monte Carlo comes along because there's been a reprocessing. Um,
Mhm.
when you need to be able to rerun that plot and get the same plot that was before, minus the fact that the Monte Carlo has been updated. And an LLM can't do that, right?
Yes, I
Your
agree.
point about the MCP is correct. I think the MCP, unless it's got an LLM behind it, but let's pretend for a moment it doesn't. That's deterministic. So if you were to code up a call to the MCP in your Python, that would be just fine because the MCP server's versioned, et cetera, et cetera. But for example, one thing I found with my work was in that Z to TT bar, different LLMs, when they were pulling out the jets and the leptons, would apply different fiducial cuts. Like in one case, it was doing an eta cut of 2.49. In another case, it was doing an eta cut of 2.3. And none of these were asked for in the questions. It just, the LM said, oh, I think I need to do this.
Yeah, which is part of what I mean. We want a trail on what decisions that it took before.
I get what you're saying about we want a trail. I guess I think it has to be more than a trail. Okay.
Yeah.
Good.
So
we beat this horse. Yes.
Well, I think that this is a super important discussion, and also, like, personally, something that I care a lot about. We are now approximately a half hour behind schedule, so I want to make sure that we don't lose Abi by having him need to leave for something else. So, Jordan, unless your comment can be 30 seconds or less, can we take it offline?
It's pretty quick. I just
Okay,
wanted
go
to
for it.
follow up because Gordon, you mentioned about CLIs versus MCPs. So I'll give you one good example of how you make this distinction. Most of the time, LLMs can use the CLI effectively. If we have something like Rusio, or UCIO, Ruxio, Rusio, however you pronounce it, the Rusio CLI is inefficient for an LLM. It not only does not expose all the information allowed for a given data set, but it also produces way too many tokens, doesn't allow for pagination, that sort of thing. You can, for example, do a Rusio-LLM CLI and make that friendlier, wrapping around the Rusio CLI to do all the same thing, or you then wrap that around a Ruxio MCP server of some kind, which I've already done. The other distinction you need to make is about user access. If you can host that server somewhere and provide delegated authorization access so that everybody can get their own information and doesn't necessarily need to be anonymous, then you can host a central MCP server. If you can easily do that because you're dealing with like X509 or something like that, you do STDIO or a local MCP server, which is effectively a command line interface locally. An MCP server hosted on the web somewhere they access by HTTP is the same as a command line interface locally. There's not really a distinction there. The distinction is more, do I need to wrap an existing command line interface or not? Most of the time, at least for HEP, the answer is going to be yes, because most CLIs that we have in HEP suck. Sorry.
Yeah. Okay.
Okay, thank you.
Thanks very much, and also thanks, Mohammed, very much for this talk. Obviously, generated lots of discussion, which I think is great. So, thanks, and then Abi, thanks for holding on. I'm sorry that we're running so late, but we'd be very happy to go to your talk next if you can still hang on and share it with us.
Yeah, thanks, Matthew. Yeah, let me just share the screen. Yeah, can you see the screen?
Yeah, we're currently seeing like the whole. Yeah, you're about to go to. Okay, yeah, perfect. So, yeah, all right, great.
Okay. So yeah, I can start when you say yeah.
Oh yeah. No. Yeah. So yeah. I guess for the recording, this is a talk on MITRA from Abi, and this is, I think, much more focused on kind of CMS for the time being, but this is also general guidance for us more broadly. So Abi, please take it away.
Okay, so thank you for the invite, Matthew. So hello everyone, I'm Abi. I'm Abhishek Mallampalli. You can call me Abi. So I'm here to present our work on MITRA, as Matthew was just telling. So like so this we are like building it as an AI assistant for CMS, but it's experiment agnostic. So okay, so before I start, I would like to say many thanks to like Professor Dasu, Tulika, David Lang, Peter, Elmer, Verena, Rafael, Lothar, and Dirk for funding this project. Thanks to Professor Ravindran Balraman's team at the AI department in IIT Madras for guidance in evolving this project, and the UW Madison computing team, Dan, Chad, Ajit, and Carl for help setting it up in the Wisconsin Tier 2 system of CMS. So the outline is, so I would try to like in the first section motivate why do we need a system like MITRA, that we are why we think it is important. And the second section would be like the system that is described, the system as described in the paper that is linked to the agenda. And some recent, and the third section would be some recent developments, things we have changed from what is described in the paper, and some future work. So at any point, like if you like, feel free to ask the question. So okay, so firstly, like why do we need MITRA? So firstly, in the LHC era, there's like more data, so more science, more documents. So HEP collaborations are bigger and more productive than ever. So the right side plot shows you the CMS publications, and the x-axis is the year, and the y-axis is the number of publications. So we can see it's increasing across all kinds of subgroups. So the amount of exciting science is incredible, and it's accelerating. So this success brings a new challenge. So there's ever-growing mountain of knowledge. So this is not across other collaborations also. So, and then there is this information maze. So for newcomers, like where do we even start searching for the information about an analysis that happened in 2016 that we want to like improve upon? So for seasoned experts, like keeping track of a lot of analysis is hard. So for example, why was a particular signal parameter not chosen in, let's say, a 2016 analysis? So this kind of information. So the core knowledge is there. It is just distributed because all of these questions are asked in the review of our collaborations, but a lot of this information is like not in the paper. So this is what I like we want to solve. So okay, these problems exist today also, but how are we able to make it work today? So it's because of many awesome people who are like helping to get this done. So like for example, conveners and reviewers, so often guiding multiple analysis in addition to their own. So from rough drafts to polished results. Then there are like object MC and statistical experts. They like they pass on knowledge like from previous analysis to the newer generation. And due to the huge workload, understandably, it takes some time for them to respond to questions. So that is, we want to see if we can, help speed it up. So, and then there is this more fun kind of thing, like during conferences, we are asked to present a collection of related analysis. So let us say like you have asked some detailed questions to some other analysis, but let's say you ask that question to the analysis team, but haven't heard back from them by the conference. So all you can do is, at the conference say that, hey, that's like a very nice question. I'll get back to you or something. So this is another thing that's there. And another more important thing is like we want to retain the whys and why nots for certain analysis decisions. So, for example, during the HLLHC era, we want to be able to know why certain decisions were taken in run 2 and run 3 analysis. So some of the people doing the analysis might actually leave the field and stuff. So yeah, and not all this information is in public papers and pass. A lot of this information is, as I was saying earlier, it's there in the detailed review, so that all analysis go through, and it's scattered in across places. So yeah, that's what we want to streamline. So this is our goal. Like if you want to sum it up in one slide, so can we like build an AI assistant to help retrieve this fragmented knowledge so that we can free up the valuable physicist analysis team time, so that they can focus on the analysis rather than searching for information. So for that, we are trying to help towards solving that problem. Like we are developing MITRA. So this is like based on retrieval augmented generation. So the vision is to get fast, accurate answers to analysis related questions backed by the source. So once we have the source, we can go back and verify like the answer. So this is that paper I just linking here. So this was presented at Lepton Photon 2025 and also NeurIPS Machine Learning for Physical Sciences 2025. So how does it work? So firstly, we want to get the relevant documents, extract information from it, create a database, and then we have to build like a system like for grounded response generation. So when we are thinking, okay, how can we build such a system? So there are some of the properties which we know that the system should have. So for example, like the system should know about analysis. So for example, if we ask it what is the CMS pencil jet analysis or something, so it should be able to find out what is the analysis we are talking about. Recognize, so the system should be able to recognize multiple ways of saying the same thing. For example, transverse momentum versus PT, they refer to the same thing. But so this is the reason why like a simple search would not work. For example, this particular property, a simple keyword search might not be able to solve. And then we want to keep the collaboration documents private. So a lot of this, so what we mean by that is a lot of this is pre-publication material. So we want this system to be useful for people like as their review process is ongoing. So since this is pre-publication, we want to keep all of this on all of this information private within the collaboration. By private, we mean within the collaboration, accessible to all members of the collaboration. And we want to keep the cost low. So why do we want to keep the cost of, so because when we build any such system, even though the cost of let us say a single API, like for asking a single question, single token, the cost might be low. But if you scale it up across many questions a single user might have, and also across many users that the collaboration might have, and also across the time where let us say this, we want the system to live through, let's say, to HLLHC. So the cost of a single token keeps multiplying by all these factors and it keeps blowing up. So that's another thing we wanted to keep in mind. So okay, these are the, so our system wants to solve all of these properties. It wants to have all these properties. So so I'll just briefly talk about some of these steps. So for creating the database, we use Selenium to navigate the internal CMS database. So basically, there's no manual downloading of all these documents. So we can scrape this internal information. And then in the paper, we used optical character recognition to extract the text. And this extracted text is converted to vectors, some high dimensional vectors. And this process is called embedding. And that is stored in the database, which can be searched. So a brief overview of how this database works. So every piece of text is represented by a vector. In this high dimensional space, similar pieces of text are closer together. That's how these vectors embedding is designed. And then the goal of this is to try to see let us say if we have some vector for electromagnetism and we subtract a vector for photon and add a vector for gluon. So what we mean by similar text is closer is we would get a vector pointing along the strong force direction. So this is the kind of idea to keep in mind. So the process of answering a question now can be translated to hey, embed this question in this high dimensional space, get the closest vector to this question. And then, so the idea is that this closest vector would contain the answer to this question, which we pass on to the LLM as context to generate an answer. So in the paper, we used ChromaDB for the database, and we use large language models to generate the response. So the size of the number of parameters of the model that we used in the paper is 7 billion parameters. So in context of today's large language model, maybe it's considered small, but yeah, that's the size. And so earlier I was telling you that we want this to be privacy and low cost. So the way we do this is the entire process runs on collaboration GPUs. So we use the Wisconsin, like UW-Madison's Tesla T4 GPUs, which is accessible to CMS Tier 2. And then embedding generation is done locally. The vector database is hosted locally, and the LLM is also hosted locally. So we are not using any external APIs. So we are not dependent on any company policies for token costs. So as I was saying earlier, that's scalable in time and user base. So, but there's a trade-off when we are doing this. We are making this choice because the models might not be so, because we are like going for smaller models like 7 billion and quantizing them to fit on our the GPUs available for the collaboration. They might not be as performant as commercial APIs. So yeah, we have to design our database and the entire framework to be able to be as robust as possible. And the design philosophy is we current in the paper for the paper version we used there's like a 2-layer database. And then mainly so the first layer searches for the analysis most relevant to the question, and then the second one dives into the analysis. The reason we wanted something like this is because for the same question we might have a different response. Like for example, for a question like what is the mass of Z prime boson, there is no specific answer for this because it depends on the search, the search that we are interested in, the particular analysis. So okay, so we designed this system, and some more details are in the paper, but I would like to present here how we evaluated this actually, because it's important to evaluate these systems to understand actually how good they are doing and what can be done to improve it. So this is there are a lot of numbers, so we don't have to look at all of them. The main thing to see is that P and K are like precision and recall, and there are two sets of queries. So what's important is and we are comparing our system against a keyword search. So keyword search is just searching without using any AI kind of thing. And MITRA is the system that we just saw. So, and there are two sets of questions. The set one has questions which are using the phrases which are verbatim with the document. So basically, since we know so set one is so the goal to see is that if our system is works for set one, that means so for example, it's able to identify, that's like a baseline, because we want it to be able to identify these phrases which if the exact phrasing is used in the question. So we see that in this case both keyword search and our system MITRA performs well, so equally well. Actually, what's interesting is at precision and recall at 5, the search performs better. But what's more realistic is set 2. So where we have questions which are rephrased. So the why I'm saying this is more realistic is that, let us say I'm interested in in knowing about an analysis that was done by another team. So I don't know what is the phrasing they used for conveying a particular idea. So this is a more realistic set because this is how we would use it in real world. So we can see that for this set, our system MITRA performs better than a simple keyword search. So the motivation to do this study was to see that, okay, is AI really needed, or are we just plugging it in because that's the new cool thing? So, and then these are some more evaluation, but that's the idea. But the thing is, one thing that we wanted to highlight here is having a wider evaluation set comprising of various analysis would be quite valuable to other teams or anyone developing such systems. So this might be something the community would, because this is effort intensive thing, maybe the community decision is needed for this one. And some more recent work. So this is what the previously what we saw, what was described in the paper. And we've been working on some improvements and new capabilities. So for example, in the information extraction, we shifted away from optical character recognition to latex-based extraction. So this is mainly to help with mathematical symbols for them to retain consistency, and also takes advantage of the fact of existing CMS workflows, because all of this information, at least the papers and stuff, they are generated in latex. So we actually have this sitting in the existing workflow. So it's better we make use of make use of this. So this thing has been done. So we upgraded the database architecture to scale better when scaling to when scaling to a large number of analysis. So this has been done. And we evolved MITRA into like an agentic system capable of iterative self-correction and performance optimization based on user interaction. So this has been tested independently. Like integration has been done part way. So this is ongoing. So we added capacity to see if we can support shift crew. So not just analysis, but also like shift detected shifts. And we started with Calo layer 1 because that's the one I'm familiar with because I took those shifts as a PhD student. So that has been done. And we improved the traceability of workflows so that this might help guide users how to improve a query if they're not satisfied with an answer. So currently what we are doing is scaling this to a small subset of analysis. So for example, starting with this subgroup of CMS and basically running some pilot tests. So this is ongoing. So far the current focus has been to test various ideas with some set of analysis that I'm familiar with so that I can know how the system is performing. So I've just have a recording of some demo here so that we can see what's the capabilities of this one. So while we demonstrate the capabilities using the CMS, what I want to say, as Matthew also pointed out in the beginning, is this framework is modular and the underlying pipeline is experiment agnostic. So let me just click this recording. Let me just open it. So hopefully this allows the sharing shows this actually. Matthew, can you see the new screen or?
Yeah, we can. It's in a. We can see it well now. It's sufficiently large.
Okay. So basically, like, let me see. Yeah. Okay. So this is how the system would look like. Like I'm just typing. So this is one of the questions which motivated me, to like develop such a system, because in one of the analysis I've been working on, this kind of question kept coming up in multiple reviews. So because this information was there it was there in the reviews but not in the paper. So for example, in the paper, many times we describe, hey, these are the parameters we chose, but sometimes we don't explain like why a certain parameter was not chosen. But that kind of thing gets pulled up in the review. So for example, like here, this is a particular analysis for CMS. So this I'm just showing the feature here, like you can search by like whatever, if you already know the analysis you're interested in, if you have the ID number, you can just search it so that you can save the compute. And we can see here it's telling you that, hey, in this analysis, in the number of extra dimensions, so and so. Here you have to trust me. This is the correct answer. This is the this I was an analysis. So yeah, that's the thing. So what's interesting to see, like how did this do this? So this is what we meant by traceability. So we can see what are the steps it took to basically reach this answer. And if we see that, hey, at some step it went to some other document which it should not have searched, then we can try to see, okay, maybe something in my query prompted it to go there, and see how we can change that. And then it also gives you sources here, but that you can follow through and like verify to see if this information is correct. So here you can see that actually the answer uses only 1 and 2 for source, but there are 4 sources listed. So we have fixed that. So what's actually happening is the system retrieved 4 pieces of information, but the generator realized that only 2 of them were needed. So right now, but the earlier in the code was just listing everything that was retrieved. Now we have fixed this, but this recording was done earlier. So this is another question, here, just like we are familiar with many other interfaces, there's like a previous history to see the chat. And on top here, like we can see what is the current context, so that we know that, hey, our analysis, this is the question we are answering about. And the same thing here, like, hey, we have asked what is the mass of Z prime in this search, and it has given you an answer that this is the mass. And we have options here to compare 2 different analyses. Instead of asking questions about a single analysis, you can select 2 of them and ask, hey, which of them has a higher MET or something like that. And we have a different mode for shifter because analysis and shifter is like kind of independent. So like this is for the shift group, and here I'm just asking like, hey, what is a Calo L1 link mask? So when we are in shifter mode, the motivation for this is we don't have to like keep track of all these analysis, and the search will be much faster. And at any point, if you think your query is, if it's not needed, you can cancel it to save compute, so that you don't waste the tier 2 resources. And this is just, we can skip this one, I think, but so there's some different steps being performed, and finally, like it's realized that only 4 are important or something. And so since we are using locally, yeah, this is, you can see here, this is a local host. So this is being done locally. And then you can see that it's giving you an answer. Hey, a Calo L1 is a link mask XML file or something. What's interesting is that there's this kind of information is present in a different wiki, which is telling you that, hey, perform this link mask only by contacting the ecal or hcal doc. So it's that's interesting that it's able to collect information from different places and give it on in one place, so that if someone taking a shift, even if they forget or if that someone new, some of this important information is always at fingertips. So this is the like demo. So back to this thing, slides. So what is the road ahead and some open questions. So while we were working on this, I had to think about some of these questions, but maybe it's like there are many smarter people in the community, and like we have to come up with some answers to some of these questions, like what is the best way to encode physics knowledge, like and is whatever scheme that we come up with, is it robust across different ways of phrasing analysis, and if it is robust, can we verify and confirm that if it is robust? So how do we do these kind of things? So and then like yeah, so later on we like there was some tests that we were doing, like how can we make the system be able to read and understand plots? This might be useful for reviews, and scale the system to a larger set of analysis and shift operations. Like how do we extend the evaluation framework, like I was mentioning earlier? And also one more thing is sometimes the information keeps changing across the review cycle. So for example, like a certain answer might have been correct in the beginning, but later on the analysis team might have switched to a different method or something. So these answers have to keep evolving. So that is another thing that we have like worked on. So yeah, and this is it. And like thanks for listening, and open to any suggestions or like ideas that people might have. Thank you very much.
Sorry, it took me a second to unmute myself, but thanks very much. This was a really nice summary talk of all of the work that you've done so far. I have some questions, but I think some other people do already as well, so maybe let's go to Andre first.
Hi, thanks. Thanks, Abi, for the talk. I was just curious, so you were showing that you had these, you were pulling up these comments from CMS review. I was curious, were you sort of to what extent were you able to access, let's say, the body of information that we do have internally? Is this just because they kind of looked CWR formatted? But so I'm curious, sort of, yeah, I guess to what extent were you able to scrape all of the information into your database?
Yeah, thank you for the question. Like so basically currently for the analysis we have we have scraped the information from the wikis. So CMS just for like someone in some other collaboration, so we have like information stored in like some files which are wiki like pages, HTML pages, and there we put in the review questions and also the answers for analysis. So currently the review, the answers that you saw, like for example, why was the n equal to 1 not chosen in the ADD scenario? So those kind of answers are got from like we got it from the Twikis. So, but yeah, and so the currently we have analysis support for like 7 or 8 that Wisconsin Madison has been involved in. So we are scaling it up to like all the SUS analysis. Yeah, and we looked at can we get information from the pub talk, but then we noticed that most of the important information from the pub talk is condensed by the analysis team in Twikis anyways. So yeah, we did not.
Yeah, I think that's true if the analysts actually keep it tricky. I don't know what the fraction of people that do. I I don't know if also like I'm this might be showing some CMS lack of knowledge, but I also don't think that all of the analyses like or I don't know that there's a centralized sort of page for all the CMS tricky pages for analyses. But maybe you
Uh,
can correct me if you have one, please send it to me because I can
yeah,
never find these
yeah,
tricky
I can
things.
tell you. Yeah, I can point you to one thing. So we had made this presentation like to CMS internal communications, and they told that they are compiling a list of such a thing, and they will send it to
Okay,
me. Yeah,
okay,
and
that would be
yeah, if I get it, I will send it to you.
that would be great because we actually sort of internally tried to do something like this by scraping pep talk, but then we got busy with some other things, so that never materialized. But then the other question is, do you do any sort of triage on the comments that you retrieve from Tricky, or do you just let it happen sort of at the end when you make the query? Like,
Can you
if that
just
makes any
repeat, please?
sense.
I
Yeah,
didn't get.
if you make any kind of triage on the contents that you scrape from these Trickies, right? Because you'll have comments like uh make the y-axis label 2 points larger, right? Or like stuff like this that's not really useful.
Yeah, yeah.
Or useful comments, but they're just not wrapped in a way that they have information like have you evaluated the jet energy scale? That kind of
Yeah,
context. So
yeah,
do
that
you
kind of
do
thing.
you do you remove these things from the
Yeah.
corpus, or do you just let it sort of sit there?
Yeah,
Um,
that's a nice question. We actually did a lot of we did try a few things here, but we thought that there are so many. This seems like a simple problem, but how do we convey? How do we represent something is useful or not, right? So that is that turned out to be very tricky. So basically, we let them sit basically in
okay.
the so
Hmm.
because there are some questions like, hey, change the spelling of this word, that those things we can, if they are organized properly, like CMS has this setup of saying like type A and type B or something. So type
Right.
A are like English language, so those we can remove. But what we noticed was many times some groups were putting type A comments in type B and stuff, so that would
Yeah.
be very tough to parse, a lot of effort. So we were like, okay, let it just sit there, and the LLM is smart enough to figure it out from our tests.
Hmm. Okay.
Yeah,
Thanks. Cool.
yeah, thank you.
Okay, great. Let's go to Jordan. I think he already had a comment in chat, but it'd be good for the recording to also get that comment if this is different from what your question is, Jordan. But I'll let you go ahead.
Yeah, my comment is actually different, but do you want me to restate what's in the chat?
Yeah, just because that won't get captured in the recording otherwise.
Oh, okay. Right, so in Atlas, at least for analysis information, we have the central database called GLANCE, GLANCE, that is run by the FENCE team, FENCE. And there's an LLM friendly command line interface that wraps that API, so we have that at least on the Atlas side. That's the comment in the chat. My question is a little bit more abstract. You have this concept of a structured database, which totally makes sense. I mean, this is what people have done for like RAG-based augmentation and things like that. But what I haven't been able to figure out is where is that line drawn, if you had in CMS the ability to do the real-time querying that you need of all the information, then you wouldn't necessarily need a factor database, right? Meaning if all of the, paper review comments and all of the different quickies were queryable from the LLM, you wouldn't necessarily need the vector database, or does the vector database give you something in addition to the lack of querying to make this work?
Okay, so the way I understand is this system is currently is defined for the way CMS currently shares information. If suppose we switch to some way like that you're saying is like automatically queryable by like LLMs and stuff like this, then maybe we have to evaluate to see like, hey, are there any like drawbacks in that system that this can fill or not? Like we don't know what that system would look like. So currently the system that we have is like not queryable. So that's the problem we are trying to solve.
Yeah, so I guess what I'm trying to understand is I think of the vector database as almost like a cache, kind of, to give you something that is queryable. Is that the only benefit you get from this? Or is the LLM somehow able to do significantly less context in addition to having the vector database? Or is it just giving you an interface to make it LLM friendly to all of the knowledge you already have?
I see. Okay, so if I understood, you're saying like, how do we design the context to the LLM is maybe like a question. Is that so? All of that goes into like the database architecture. Like, how can we reduce the number of searches it performs to zone in into the relevant analysis and keep the context as minimal as possible so that we don't give it scope to hallucinate or something. So that is what that's what we designed in the in the backend, and that's the database infrastructure. But yeah, I don't know. So the context is as minimal as we think it is needed. Yeah, I don't know if that
Okay.
answered your question. Yeah.
Yeah, that makes sense. If suppose CMS if you had some ability to query this quickie on the fly, would you still store that quickie information in the vector database, or would you just query the quickie?
So that, if I already for one particular, I showed you that if we are already sure about a particular analysis, right? In that case, I know that, hey, the answer for this particular analysis is going to be in this Twiki. So I can just query the Twiki. But sometimes the answer to a particular question of an analysis might be in the Twiki, might be in an analysis note, or might be in the paper. So you can either query all three systems, or you can have an integrated system. You query it and it knows like it can save you time by searching across. And there is another like deeper one. What if we don't know the analysis actually, which we are querying or something? So I don't know if that is another aspect, right?
Okay, I see. That makes sense.
All right. So, well, I did have another question. I believe that it's already past 10 p.m. local time for you at the workshop that you're at, so I think I can probably just ask this on follow up on the IRIS-HEP Slack. But thanks very much for this talk, and since I don't see any other questions, I think we'll go ahead and end this topical meeting here. It's pretty clear that this was that these three talks generate a lot of interest and comments. So I'm sure that we'll have a second or further kind of talk in the series or topical meeting in the series. So for people who are interested, please sign up for the IRIS-HEP announcements mailing list. And yeah. Okay, thanks very much for joining, and talk to people online soon about all of this work. And thanks very much to our three speakers today.